factor that we're going to investigate with the Chatelier's principle. So remember, Le Chatelier's principle is the idea that if we have a system at equilibrium, if we cause a stress, so we change a concentration, we change the temperature, we change the pressure, our equilibrium is going to shift to oppose that change. So for pressure, if you guys remember to your unit on gases, we really only talk about pressure with gases. Okay, so pressure will only affect our equilibrium when gases are present. So we have two things that can happen to our pressure. We can increase it and we can decrease it. So if we increase our pressure, remember, we can increase our pressure or our number of collisions by decreasing our volume. All right, so we can, if we cause an increase in pressure or we cause more collisions within that container by decreasing our volume, our equilibrium is going to shift to the side with fewer gas molecules. And again, we're only looking at gas. Okay? And the reason why that is because we want to lower the number of collisions that we're having. Okay, so if we increase the pressure, we want to undo that increase in collisions. So we're going to move to the side with fewer gas molecules. Okay. The other thing we can have is we can cause a decrease in pressure. So there we can have less collisions that are caused by an increase in volume. Okay, because remember, if we increase the volume, our particles have more space to move, there's less collisions. To undo that change, our equilibrium is going to shift to the side with more gas molecules. Okay? Because by shifting the side with more gas molecules, we're more likely to have those collisions that we initially lost. Okay, so big idea here, increase in pressure, that will cause our equilibrium to shift to the side with fewer gas molecules to cause less collisions. And if we decrease the pressure, we're going to move the side with more gas molecules to regain our original number of collisions. Okay, so if we look at this equilibrium system here, we have nitrogen dioxide in equilibrium with dinitrogen tetroxide. So for instance, if we increase the pressure, we need to determine what side has fewer moles of gas. Because if we increase the pressure, we're going to want to lower those number of collisions. So if we look at our equilibrium system, our reactant side has 2 moles of gas. Okay, and we can tell that by our coefficient. And our product only has 1 mole of gas. And again, we can tell that by our coefficient. Okay? So if we increase the pressure, we're going to want to move to the side with fewer gas molecules. So we're going to shift right, because we want to lower our number of collisions. Okay. However, if we had the opposite, if we decreased our pressure, and again, remember, we decrease our pressure by increasing volume, give those particles more space to move. Here, we're going to move to the side with more moles of gas, because we want to regain those collisions that we're losing by increasing the volume. So here we are going to shift left and start making more reactants. To undo that stress, to again increase our number of collisions. Okay, so when we're looking at pressure, we're really just looking to see which side of our reaction has more moles of gas. We were just talking about. So we can see if we decrease the volume, we're going to increase our number of collisions. And when we increase our number of collisions or increase our pressure, our equilibrium is going to shift towards the sides with fewer moles of gas. So since our product only has 1 mole of gas, we're going to shift to the right and start making more N2O4 in order to, again, reduce the number of collisions that we have. Okay? So if we increase the pressure, we're going to shift to the side with fewer moles of gas. However, if we increase the volume and decrease the pressure, we can see that we are going to shift to the side with more moles of gas in order to regain our original number of collisions. So in this scenario, we shifted left and started making more NO2 since our reactants had 2 moles of gas due to that coefficient. So if we decrease the pressure by increasing the volume, we're going to shift to the side with more moles of gas so we can regain our original number of collisions. So a big idea when you're looking at pressure on the Chatelier, look to see what side has more moles of gas versus what side has fewer moles of gas. Yeah, make sure that we don't get cooled. So we have this equilibrium system where we have 2 moles of A, which is a gas, plus 2 moles of B, which is a solid, and equilibrium 3 moles of C as a gas. So remember, if we increase pressure, we're going to want to shift towards fewer moles of gas to reduce our number of collisions. Okay, so the key here is that we want fewer moles of gas. Okay, so if you look at your equilibrium and you are dealing with pressure, if you see anything that's not a gas, you can kind of ignore it. Okay, because it's only those moles of gas that will affect our number of collisions. So if we look at our reactant side, we're going to see that we only have 2 moles of gas. Because A is our only substance or only reactant that is a gas. On our product side, here we have C, which is a gas, with a coefficient of 3. So on that product side, we have 3 moles of gas. So that means even though our reactants have more moles overall, looking only at gases, the reactants have fewer moles of gas because A is the only gas on that reactant side. So in this scenario, to reduce our number of collisions, we are going to shift left to make more reactant. Or in other words, we're going to favor that reverse reaction in order to reduce our number of collisions. Okay, so when you're looking at number of moles, just look at your number of moles of gas for pressure. Okay, because liquid, solid, aqueous, they don't impact your number of collisions. So that is all the notes for today for Le Chatelier. I am going to walk through the exit ticket from the other day if you guys want to stay on and kind of watch that. But otherwise, you guys should be good to go to finish up your homework and let me know what questions you have. The ticket that you guys turned in on Tuesday. So looking at that first one, I think most people did a pretty good job seeing that based on the equilibrium constant value of 0.18, that your reactants were going to be favored at equilibrium. Since that KEQ value was less than 1, that meant that we needed to have a larger number or a larger concentration on the bottom of that expression, which is where our reactants are. Okay, so since our KEQ value is less than 1, we have more reactants at equilibrium. Looking at part B, I think honestly the biggest mistake here was we didn't realize that part B coincided with part A. So we had the same reaction as we did as in part A, and we're going to have the same KEQ value, which they told us is 0.18. Okay, so looking at what we're given for part B, we know we have 6.15 moles of Cl2O gas and 6.15 moles of steam in a 5-liter flask at a certain temperature. And we want to calculate the equilibrium concentrations. Okay, so initially we have this many moles of gas in 5 liters. So remember our unit for our ice table and our hint that we need to set up an ice table here is that we're given initial values, not equilibrium values. is going to be molarity. Okay, so if we're using an ice table, since we are given initial values, we need to calculate our molarity here. So remember, molarity is equal to moles over liters. So if we know we have 6.15 moles in 5 liters, that means our concentration, our molarities of our reactants initially would each be 1.23. That's always fun. 1, 2, 3. So since that is our initial concentration of each of these substances, we're going to put those in our initial row for our reactants. That's how much we have before we reach equilibrium. It doesn't say we start with any HOCl, so we're just going to leave that as 0. Okay, so now we need to determine how much each of these substances are going to change by. So remember, since we're in equilibrium, we are constantly producing our products, and our products are breaking down to make our reactants. So we cannot say we're going to completely use all that 1.23 molarity of our reactants. We actually don't know how much we're going to use up. So we're going to leave that as minus x. Since it's our reactants, they're being used up. And since they have coefficients of 1, it's only going to be minus 1x. Whereas for our product, that has a coefficient of 2. So instead of just being x, it's going to be 2x, because we don't know how much products we're going to have at equilibrium yet. And since it's a product, we're going to be producing it, so we want to leave that as a plus in our change row. All right. So then to find our concentrations at equilibrium, for our reactants, we know we started with 1.23 molar. We used up x molarity, so we're left with 1.23 minus x at equilibrium. For our product, we started out with a molarity of 0. We increased our molarity by 2x. So 0 plus 2x would give us an equilibrium concentration of 2x. Okay, so since they don't give us any equilibrium concentrations or any other way of finding what that value x is, that is our hint that we're going to need to use our equilibrium expression. So a good first step is to write the equilibrium expression. Remember, that's products over reactants. So our product here is HOCl. And since, again, we have that coefficient of 2, we're going to need to square that concentration. That was another big mistake in this one. And then we'll divide that by our concentration of Cl2O and our concentration of H2O. Each of those have a coefficient of 1, so we don't need to worry about an exponent there. All right, so here we'll plug in what we know. We know at equilibrium, our K value is 0.18. We know at equilibrium, our concentration of HOCl is 2x. Make sure you guys square that as well, since we still have that coefficient. And then we'll divide that by our concentration of our reactants at equilibrium. Since they're both the same, I'm going to make that easy on myself and just make it 1.23 minus x squared. Once we're here, the algebra is done. Or sorry, the chemistry is done. Now it is just algebra. So since we have a squared on the right-hand side, a good first step is to take the square root, make that a little bit cleaner, a little bit easier for yourself to work with, and we'll get 0.42 is equal to 2x over 1.23 minus x. All right, so now we have an x in our denominator. So a good next step is going to be to multiply each side by that denominator. So you get 0.42 times 1.23 minus x is equal to 2x. Okay, because yeah, we want to get rid of that fraction. Okay. So from here, since we have 0.42 times the quantity 1.23 minus x, we're just going to distribute that 0.42. Okay. Again, just make it a little bit easier to work with. And when we do that, we'll have 0.517 minus 0.42x is equal to 2x. Right. From here, now it's nice and clean. Now we're able to combine those like terms. So we want to get x on one side of the equation. So we add 0.42x. Left with 0.517 is equal to 2.42x. And then our last step to find how much those concentrations are going to change by is to divide each side by 2.42. And we should find that our x value is 0.21. Okay. So be careful here. We did all that work, and all we did was solve for x. We just saw by what ratio are those concentrations going to change by. To get our actual concentrations at equilibrium, we need to plug that value for x back into the equilibrium rows of our ice table. Okay. So to get our concentration of Cl2O and H2O at equilibrium, we'd want to do 1.23 minus x, or minus 0.21. Okay, since they each had a coefficient of 1, they're just subtracting that value of x. And we should find their equilibrium concentrations is 1.02 molar. Okay. Likewise, to get our equilibrium concentration for HOCl, since that one had a coefficient of 2, we're going to have a twice as great of a change. So 2 times 0.21 to get an equilibrium concentration of 0.42 molar. Okay, so key things there, you guys. Make sure you first change your moles into a molarity. And then since you're given an initial value, plug those molarities into your initial row. Find how much those initial values are going to change by. Remember, always subtract from your reactants because you're using those up. Add to your product since you're making those. And to see how much they're going to change by, look at those coefficients. Add your initial interchange row to see how much you have at equilibrium. And then since we have no other way to solve for x, that's our hint. We need to write the equilibrium expression. Okay. We do that algebra, we solve for x, and then once we get x, we plug that back into our equilibrium row. Okay. So that one was a little long. Awesome, awesome, awesome. All right, so then that second one, here we have, oh, I forgot my equilibrium arrow. 3 H2 reacting with 1 N2 to make 2 NH3, and the system is in equilibrium. So this one was nice because they gave us our concentrations. So we don't need to change anything into molarity. Right. So they tell us our initial concentrations are 1 molar. So since we see that word initial, that's a hint that we need to set up our ice table. So we know initially our concentration of H2 and our concentration of N2 are both 1 molar. It doesn't say anything about having NH3 initially, so we're going to make that 0. All right, if we read on, it says once equilibrium is reached, it is found that the concentration of NH3 is 0.4 at equilibrium. So since we know our equilibrium concentration of NH3, we can put 0.4 into that equilibrium row for NH3. Awesome. All right, so our end goal is going to be to find the equilibrium constant. So that means we're going to need to know our concentrations at equilibrium. All right, so we're going to look to see where we have the most information. We're given the most information about NH3 because we know how much we start with and how much we have at equilibrium. So if we start with 0 and we end with 0.4 molar, that means we had to create 0.4 molar NH3. Okay. All right. So for H2 and our N2, we don't know right now how much of those we used, but remember, since they're reactants, we're going to use those up, so we're going to subtract x from them. Since the H2 has a coefficient of 3, we're going to make that a minus 3x, okay, because we're going to use up 3 times as much H2. So then at equilibrium for H2, we have 1 minus 3x. For N2, we have 1 minus x. So what we really need to do is find out what x is. So our tool to do that is to look at our NH3, since that's where we know the most information. So since we know we made 0.4 NH3, and NH3 has a coefficient of 2, that tells us that that 0.4 is going to be equal to 2 times x, or 2 times that ratio that we're changing by. Okay, so if 0.4 is equal to 2x, that means x just has to equal 0.2 molar. Okay, so each substance will change by a factor of 0.2. All right, so now that we know what x is, we can plug that into our equilibrium row. So for H2, we have 1 minus 3 times x, or 3 times 0.2. So we're left with a molarity of 0.4 at equilibrium. For N2, we had 1 minus x, or 1 minus 0.2. So at equilibrium, we had 0.8. And then we already knew what NH3 was at equilibrium. All right, so we're not done here because we're looking for equilibrium constant, not just the concentrations. So we need to write our equilibrium expression. So remember, that's our products over our reactants. And since the NH3 has a coefficient of 2, we're going to square that concentration. H2 has a coefficient of 3, so we're going to cube that concentration. And then N2 has a coefficient of 1, so we don't need to raise it to any power. All right, so now that we know what our expression is, we're going to plug in those equilibrium values into that expression. Remember, K is for equilibrium, so we can only use equilibrium values. So for NH3, we know our concentration is 0.4. Make sure you square that because of that coefficient of 2. H2 has a concentration of 0.4 as well, and we're going to cube that because the H2 has a coefficient of 3, and then N2 has a concentration of 0.8. When we plug that in our calculator, we should get a K value of 3.125. All right. So let me know what questions you guys have on the exit slip. I hope that helped. But yeah, we'll see what questions we have in the upcoming days to get ready for our test on Tuesday. All right. Hope you guys have a great day.